Numerical values of measurements, part 2. So in this video, we are going to continue talking about significant figures, and in the end, we are going to talk about accuracy and precision. We've learned how to count the number of significant figures for a number. Now we need to know what if we add two numbers with different significant figures. What does the final answer, how many significant figures the final answer should have? So the first thing we're going to learn is addition or subtraction. So for addition or subtraction, the rule is the lowest number of decimal places. Okay, and decimal places are the numbers after the decimal points. Okay, so the first thing you need to do when you want to do the addition, for example, we have these two numbers. Okay, so you write these two numbers, you align them where the decimal point is, and you start doing your addition. You get your number, and then you drop with the lowest number of decimal places. So this one have 3 decimal places, this one has 1 decimal place, so the answer should have 1 decimal place. So remember, for addition or subtraction, we do not think about number of sig figs for a moment, okay? Just think about number of decimal places. The final answer might have less or more significant figures than the other two numbers. And that is not what we are focusing on, addition or subtraction. We are just looking at number of decimal places, okay? So the answer should have the lowest number of decimal place, okay? So this one have 3 here, this one has 1 decimal place, so the answer should have decimal place. How many sig figs does it have? So if we cut it from the 1 decimal place, it should be this. So it has 3 sig figs. Okay. Let's see the bottom example. So this is a subtraction. Again, the same thing. First, you line them up where the decimal place is. You do your subtraction, and then you drop the lowest number of decimal places. Okay, this one has 2, this one has 4, so the answer should have, this is 2 and this is 4, the answer should have 2 decimal places. Okay, how many sig fig does it have? It has 2 sig figs. 2 sig figs. So number of sig fig might be different than the other two numbers, like in this example, for example. So the first number, it has, how many sig fig does it have? It has 3 sig figs. The second number has 1, 2, 3, 4, 5 sig figs. Sorry. It has 5 sig figs. Okay, but the final answer has 2. So it might be less than the other two or more than the other two, and that's not what we are focusing. The number of decimal places is ruling the final answer. Okay, so for addition and subtraction, you look at the decimal places, and the answer should have the fewest number of decimal places. Multiplication division might be a little bit simpler or easier. So because usually the confusing part is addition or subtraction, because it's on the decimal place and we are talking about significant figures, so sometimes students just mix up those two and they go with the number of significant figures. For addition subtraction, we just count the number of decimal places and then go with the lowest number of decimal place. In multiplication division, I think it's easier. So you just count the number of significant figures of those two numbers. If you have 3 numbers, those 3 numbers, no difference. And the number, the final answer, should go with the smallest number of significant figures. Okay, so in this example, for example, we have, how many sig figs do we have here? we have 3 sig figs here, and here we have 5 sig figs. So how many significant figures the answer should have? It should have 3. Okay, so we start counting from the first non-zero digit from the left. So it's 1, 2, 3. You have to cut it from here. If this number, next number, is 1, 2, 3, 4, we round it down. We keep it as this number as 5. If it's 5 or higher, we round it up. Okay, so this is 3, so we have 16.5. Okay, it's the same thing with the division as 2. So for division, again, the same thing. How many sig figs do we have here? We have 2 sig figs, and here we have 5 sig figs. So how many sig figs the answer should have? It's 2 and this is 5, so the answer should have 2 sig figs. So we start counting from here, from the first non-zero digit. These 2 are leading zeros and they're not significant figures. So we start counting from here. This is 1 and this is 2. So we have to round it from here. Since the next number is 6, so we round this up. So it's 61. So the answer is 0.061. Now that we know the rules for multiplication, division, and addition or subtraction, what if we have a multi-step calculation? So the first thing you need to know is the order of the processes. The rule that is called PEMDAS. So PEMDAS tells us the order of the processes. So P starts with parentheses, exponential, multiplication, division, and then addition, subtraction. It means we have to do these processes in order. So if we have an example like this, so the first thing you need to do, if you have a ratio like this, the first step is to draw. If it doesn't have parentheses, you have to put the parentheses yourself, okay? So you do whatever inside the parentheses first, and then you go, if you have exponential, you do the exponential. If you don't have, then you go to multiplication, division, then in the last step is the addition, subtraction, okay? So in our example, so we have parentheses on the top, so we have to do the subtraction first, okay? So to do the subtraction, the first step, we align them where the decimal place is. So the decimal place is here. So it's 9, 1 in here, and 20, 22, okay? Subtraction. So you do the subtraction, it's 0 here, so it's 4, this is 10, makes it 9, 6, 14, and it's 5, 4, 0, okay? Or you can also use your calculator to find the result, but you have to make sure that the decimal point should be right under the decimal point. Okay, so I put this 0 here, it was not there, so we know that the rule for addition, subtraction is the smallest number of decimal places, so it was right there, so we can cut it from here. So something that you have to remember is that before the last step, you do not round it up, but you have to keep track of the significant figure. So the result for that is 4.59. But is this 9 a significant figure? No. So what you need to do is to underline the last significant figure, so that you know in the end how many significant figure you have in your result, but you do not round it until the last step. You use the whole number. Okay, so you have 3.99 on the bottom, and then you do the division, and I'm doing it right now in my calculator. Divided by 3.99. Oops, I made a mistake. 4.59 divided by 3.99. Okay, so when you put this number in your calculator, it gives you lots of decimal places. Okay, I write 4 of them. 1503, but the next number is 7, so I round it up to 4. Okay, but how many sig figs should we report? So you have a division, and the division says the result goes the smallest number of sig figs, right? So how many significant figures do you have in the denominator? You have 3. How many sig figs do you have in the top? 2 or 3? Well, you write 3, but that's why we underline the last significant figure. So actually this number have 2 significant figure. Okay, so the numerator have 2, the denominator have 3. So how many sig figs should go to the final, to the result? It should be 2 significant figures. So we start counting from the first non-zero digit from the left. So it's 1 and 2, so we have to cut it from here. Since the next number is 5, so we have to round up. Okay, therefore the result is 1.2. Let's have another example here, and we will have lots of example in the recitation. So I'm just thinking about random numbers right now. So 4.56 divided by 3.47 plus 3.6426. Okay, so if we have this, and sometimes we have more processes, like you might have multiplication at the top. Okay, so the first thing you do is, if you do not see the parentheses, you have to put the parentheses yourself. Okay, if you have a ratio, if you have a division like this. Okay, so PEMDAS says do the parentheses first. So the top one is just a number, just leave it like that. The bottom one is addition, so we have to do the addition. So you, as I said, you line them up where the decimal place is. So after decimal place, 4, 2, 6, and it's 3 point that. Okay, and it's addition. Okay, so we add them. 6, this is 9, this is 8 decimal place, and that's 4. Okay, so how many sig figs should this one have? So we say we cut it where the smallest number of decimal place, so we should round it from here. But do we round it? No, we keep it like that because we are not done yet. Okay, so on top we still have the same number. Bottom we have 4.896, but we underline the last number of sig fig, so we know that how many sig figs we have. Okay, so I think I have to erase this part. So okay, so I have to do the division. So you do not round it, you keep the whole number for the process. So 4.56 divided by 4.896, and the number is something with lots of numbers in my calculator, but I only write 4 digits after the decimal place. Okay, so how many sig figs should I put for the final result? How many sig figs do I have on the top? 3. And how many do I have in the bottom? I have 3. Again, I write 4, but I have 3 sig figs. This is the last significant figure of this number. Okay, so both of them have 3. How many sig figs should the answer have? Yes, 3. So we're starting with the first non-zero digit. We do not count this because it's 0. So we start from here, 1, 2, and 3. So we have to cut it from here. Since the next number is 4, so we do not round it up. So the answer is 0.931. Okay. And we will have more examples in the recitation about this because this is a very important part of this course. Okay, so precision and accuracy. Where do we get the precision and accuracy? It's coming from the uncertainty in the results, okay, in our measurements. And where does this uncertainty come from? It might be from a limitation of the instrument. Maybe the instrument is not accurate enough, or it's not working in the real world. Nothing works ideally, right? So we might get some errors, or yeah, I can call it error. So it might be experimental design. If you think about our first lesson, scientific methods, we come up with a hypothesis, then we design an experiment to support the hypothesis. Maybe there might be some problem in the experimental designs, and you get a different result than you expected. Or it might be the experimenter. The person might have some errors that get a different result. Or nature's random behavior. You might get different behaviors, and you might get a result this day. Tomorrow you try it. It will be a little bit different. Okay. So accuracy and precision. What does that mean? Accuracy tells you how close your measurement is to the actual value. For example, if I give you a sample that weigh 10 grams, have the mass of 10 gram, and you weigh it and it's like 10.1, for example, how close you are to the accepted value is your accuracy. If you give me it's 8 gram, you're far off. Okay, if you're close to the 10, that shows you're accurate. But what is precision? Precision is how close repeated measurements are to each other. So I give you the sample and I want you to weigh it 4 times, okay? If your 4 measurements are very close together, it means your measurement is precise. It might be, you might have 4 measurements which is very close together, but all of them are close to 9, for example, but the actual value is 10. It means that you're precise, that you get around 9 every time, all 4 times, but you're not accurate because the actual value is 10, but you're weighing it as 9. Okay, so let's see some example in the next slide. So this is exactly the same example I was talking about. So there was a lead block that with a known true mass of 10 gram, okay, and they gave it to 3 students, student A, student B, and student C, okay, and they want them to do it in 4 tries, okay. Student A had these numbers, student B and student C, okay. You see here the average. Which one of these have closer average to the accepted value? You see this one is closer, it's 10.0901, and then we have these two, okay. But if you look at these numbers, so this student C have 10.03, 9.99, 10.03, so it seems like it's very close together. All these 4 data are very close together, and it's also close to the accepted value, okay. So it's both precise and accurate. If you look at student B, you see that it's 9.78, 82, 75, and 8. Seems like all 4 values are very close together, so it seems like it's very precise. But is it accurate? Well, it's not that off, but still it's 9.79, so it's not that accurate, but it's very precise. In the first student A, you have 10.49, you have 7.7, 9.79, 9.72, and 10.31. So this is not close together, so it's not precise, and the result, the average, is 10.13. okay, it's not that off, but it's not as accurate as the third one, and it's not even precise. I mean, all these 4 are far from each other. So let's see all of these results in graph in the next slide. So this is to sum up what we just said. So The measurements are said to be precise if they are consistent with one another. That's precision. Or it's said to be accurate if they are close to the actual value. So these are the results for student A, B, and C. So you see in the first one, this blue line here is the true mass, it's 10, and you see these results, they are not close together, and the average is over here. Okay, that is the average. So it's not precise and it's not accurate because it's not close to the accepted value. So inaccurate, imprecise. Student B, you see all of these values are very close together. The average is right here. So it's very precise, but it's not accurate. So inaccurate, but precise. Okay. The third student, you see all the results are very close and the average is right next to the true value. Okay, so it's both accurate and precise. Where does these errors come from? So the error might be a random error or it might be a systematic error. Okay, a random error is an error that has the equal probability of being too high or too low. Okay, imprecision caused by random error. So if the accepted value is here and one of your measurement is here, one of them is here, one of them is there, one of them is there. So you see it's a random error. It might be too high or too low, okay? And the random error is going to cause the imprecision because your data is not close together because it's random, right? So random error cause imprecision. Random error should average out with enough measurements. So if you have enough measurements, so in here we are talking about 4, but sometimes in your research you might do it like, I don't know, 5 replicates, 6 replicates, and sometimes more, excuse me. So since it's random, one of them might be here, one of them might be there, so it will average out, and your average should give you something close to the accepted value, which makes it accurate if everything else is fine. On the other hand, systematic error is an error that tends toward being either too high or too low. If there is something wrong, for example, I don't know, I'm just thinking about an error. You have to weigh something for 2 grams, but for some reason you weighed 1 gram. If you do it 100 times, you still do the same thing. So if the accepted value is here and you do it 100 times, by doing this mistake, all of your result is going to fall here. Okay, it doesn't matter how many times you're going to do it, because you're doing it wrong, all the results are going to end up here. Okay, and that's called systematic error. It's an error in your design. It's an error in it might be in the instrument, like the instrument might have some error that give you, I don't know, if it's doing a measurement, it's giving you a lower result than the accepted value. So even if you do it 100 times, it's going to be the same thing, okay? So the result you're going to get with the systematic error gives you inaccuracy, okay? If the instrument or the experimenter is precise, like doing everything else right, okay? So if you do 100 times the same experiment, you're going to get the same result, like you're going to get data around this point, okay? It's precise, it's close together, but it's not accurate because the accepted value is here. You have a systematic error that gives you a wrong result, okay? So systematic error gives you inaccuracy, okay? And well, the systematic error do not average out with repeated measurement. As I said, if the problem is a systematic error, it doesn't matter how many times you're going to do it. It's going to give you a result that average out somewhere here, for example. So that was all about precision and accuracy. So can you tell me, in this archer, is it accurate or precise? If you choose B, then you're right, okay? So you have 3 experiments and you see all of these three are very close together at the same point. So what does that tell us? Is it precise or accurate? So when all your measurements are close to each other, it means that measurement is precise, okay? But is it close to the accepted value? So in this example, we want to hit here, but we do not hit here, we hit there, okay? So it's not close to where it should be, okay? So is it accurate? No, this is talking about accuracy. So it's not accurate, but it's very precise. So inaccurate and precise. So it's B. Okay, that was the end of our video.